All right, let's start section 2.2. 2.2 is about higher degree polynomials. Higher degree polynomials just means things that are bigger than x cubed. I'm sorry, x squared. So we got our feet wet on x squared. We know darn near everything there is to know about those x squared functions. So let's up the ante. Let's find out what we can learn about higher degree polynomials. Like x to the 25th. How about that? Objectives. We want to be able to use transformations to draw graphs of polynomial functions. We want to learn how to use the leading coefficient test to determine the end behavior of graphs of those higher degree polynomial functions. We want to be able to find and use zeros of polynomial functions because that's going to help us graph them. And we want to be able to use what's referred to as the intermediate value theorem to help locate zeros of polynomial functions. What we're going to focus on in this video is the characteristics of polynomials. And as you know, polynomial function is any equation of this type. And you know, we have to write it out in a generic form so that it fits everything. But in essence, all of these a terms are just coefficients. They're just numbers. And x to the n is our highest power. And then it goes to x to the n minus 1 and so on. Okay, so I mean this could be 15x to the 20th plus 13x to the 19th plus blah blah blah, and in the end there's just a number at the end, you know, whatever that may be. Great, fine. We have tons of terms that we need to figure out, but in essence it really just boils down to things that we've worked with before. A second degree polynomial, which is what we did in the first section of this chapter, is x squared plus x plus a number. Could have a number in there, could have a number in there. But everything that we learned about the quadratic, we can learn a lot of those same things for higher degree polynomials. All right, so what are some things that we know about these polynomials? What are those characteristics? All right, well, there's two graph-wise that are of significance to us. First of all, there's a higher degree polynomial right there. It is continuous. That means that it stretches from negative infinity to positive infinity on the x-axis. And there are no gaps anywhere. We spent a lot talking about continuity in calculus class. That's why this is called pre-calculus class. But even though there's no arrows drawn on this thing, it goes on forever that way. So it goes forever in that direction, and it goes forever in that direction. Continuous means that there's no holes in it, no gaps, anything like that. So if you were to take your pencil and put it on somewhere on the curve, excuse me, you could trace the curve without having to lift your pencil off the paper. That's what continuous means. All right, and it may not seem like much, but that's kind of a big deal. The second thing is that they're smooth curves. There's not real sharp points anywhere. Okay, when we had our x squared function, it was a smooth curve on the bottom of it. That's the way all of these are. Excuse me. Okay, so we already know what the graph of y equals x squared looks like and the graph of y equals x to the third. They happen to look like this. And I want you to pay attention. All those 1, 1 spots that I talked about, still want you to keep those things in mind. All right, well, why did I bring those up? Because when we have higher degree ones, if we have x to the fourth, x to the fifth, those graphs are actually very, very similar to the other two. They look like this. They still go through that 1, 1 spot. All right, the only difference is that they're flatter on the bottom or flatter in the middle. Okay, the dotted line represents x squared. This is steeper in this area, but it flattens out a lot more than the x squared graph. Okay, in the case of x to the fifth, it's steeper right there outside those 1, 1 points, but it's a lot flatter in between. All right, and if you did x to the seventh, it would be even flatter. X to the ninth, flatter yet, and so on. So what I want you to take away from that is that the higher powers have flatter bottoms near the vertex, and then they rise sharply, yet they still hit those 1, 1 spots. Okay, that's it for this one. Not a whole lot of information, but it's still valuable. Adios.